This screen is showing one flat shade of grey. So why can you still see a taskbar at the bottom? The window is closed, the game is gone, no menu is being drawn there. Yet its outline has returned as a dim ghost. The screen has not saved that picture as a secret file. The picture changed the screen. Every bright OLED subpixel makes its own light. If the same icon keeps asking the same group of subpixels to glow, those subpixels accumulate more electrical and chemical work than the ones beside them. Eventually, they cannot produce quite the same light from the same instruction. On a uniform grey image, that difference becomes visible. You are looking at the electrical history of the panel. That is burn-in. The name is slightly theatrical. Nothing has been branded onto the glass with a tiny flame. The lasting mark is uneven physical aging. There is also a temporary look-alike. After a bright, high-contrast image, an OLED can show faint image retention that fades with time or after the panel's normal maintenance. Permanent burn-in survives the content change because the pixels no longer respond equally. The useful question, then, is not simply whether OLED can burn in. It can. The useful question is, what does an image have to do to become part of the screen? An OLED subpixel is a stack of very thin materials between electrodes. When current flows, electrons and positively charged vacancies, called holes, enter the organic layers. They meet, form an excited state, and part of that energy leaves as a photon. That is the beautiful part. Electricity becomes light without a shared lamp behind the picture. It is also why every part of the image has its own workload. Inside the emitting layer, charges and excited molecules do not complete every encounter perfectly, forever. Operation gradually creates molecular defects. Some trap charge. Some provide routes that waste excited energy instead of releasing it as useful light. Researchers often call these quenching sites. As those defects accumulate, light output falls and the electrical behavior of the device changes. The exact chemistry depends on the emitter, the surrounding materials, the device structure, current, and temperature. There is no single molecule that explains every commercial OLED panel. At screen scale, however, the result is wonderfully rude in its simplicity. A well-used subpixel becomes less efficient than a less-used neighbour. If every subpixel aged at exactly the same rate, the whole display would slowly become dimmer, and you might barely notice. Burn-in becomes obvious because normal pictures do not distribute work evenly. A news ticker uses the same strip, a game parks a health bar in one corner, a desktop leaves its taskbar where taskbars have apparently decided to live forever. The moving parts of the image share their work across millions of pixels. The fixed parts keep sending the bill to the same address. Imagine that every subpixel carries an odometer. It does not count hours alone. A useful aging estimate also cares about how brightly the pixel was driven, for how long, at what temperature, and through which color-producing materials. 1 hour of a dim, changing film is not equivalent to 1 hour of a white scoreboard fixed at maximum brightness. Calendar age is a poor substitute for workload. This is why a static image does not have to sit untouched for 1,000 hours in one heroic act of negligence. A channel logo shown for 3 hours tonight can return to the same pixels tomorrow, and the next day, and the next 1,000 days. The exposure accumulates, even though other pictures appeared in between. Black areas create their own imbalance. On an OLED, black pixels emit little or no light. If black bars stay in the same place while the center of the panel works, the center ages more. The bars did not burn in. The rest of the screen moved away from them. Color complicates the map further. Red, green, and blue emission systems do not necessarily age at identical rates. Blue OLED stability in particular has been a long-running materials challenge. Commercial displays use different emitters, filters, quantum dots, subpixel sizes, drive strategies, and compensation systems to balance those differences. So an OLED phone, an OLED television, and a QD-OLED monitor should not be treated as one interchangeable specimen. Even two panels of the same model can vary. This is also why nobody can give you an honest universal sentence such as burn-in begins at 5,000 hours. 5,000 hours of what? At which brightness?
On which panel? With which static shapes? At what temperature? And did the display complete its maintenance cycles? Without those details, an hour count is not a prediction. It is a calendar wearing a lab coat.
Long-term burn-in tests are valuable because they force small differences to become visible. They are dangerous when their conditions are forgotten. In an older RTINGs experiment, 6 2017 LG OLED televisions ran repeated 5-hour on, 1-hour off cycles. Different sets showed live news, general television, football, and recorded gameplay. Most were adjusted to about 200 nits. One news set ran much brighter. The fixed news graphics produced clear burn-in much earlier and more strongly than varied content. After almost 10,000 hours, even the high-risk football game interface began to leave a grid pattern. The important result was not a magic number. It was that repeated geometry and brightness changed the outcome. Then RTINGS compared a 2017 OLED with models from 2020 through 2023 at the same 10,500-hour CNN checkpoint. The newer group did not show a consistent reduction in permanent image retention. That sounds like 9 years of engineering achieved nothing. It did not. Each television ran at its own maximum SDR brightness. The panels were not matched to the same light output. Newer OLEDs were substantially brighter and more efficient, so some material and engineering gains were spent on producing more light, rather than a cleaner result under this particular test. The comparison also did not include panels from 2024, 2025, or 2026. It cannot tell us that a television released this year is no better than one from 2017. The severe test eventually ran CNN for 18,000 hours. That equals roughly 10 years at 5 hours per day on a clock. It does not equal 10 years of films, games, menus, sports, and a news channel sharing the screen. In RTINGs images, the persistent damage concentrated where the static ticker and logo repeatedly lived. Areas with varied content did not show the same visible burn-in. A desktop monitor can create a different but equally recognizable fossil. Monitors Unboxed deliberately used one 2024 QD-OLED monitor for more than 6,000 hours across 2 years, heavily weighted towards static desktop work. Uniformity tests revealed the taskbar, window boundaries, and other repeated structures. That is excellent evidence that a static-heavy desktop workload can mark a modern panel. It is still one panel under an intentionally punishing pattern, not a countdown timer for every OLED monitor. Torture tests answer, can this usage pattern cause burn-in? They do not answer, what percentage of ordinary owners will see it by Tuesday? Modern OLEDs do not sit politely while you age them. They cheat. Pixel shift moves the whole picture by a small amount, spreading sharp edges across neighboring pixels. It helps with thin logos and interface lines. It cannot make a large static rectangle stop being a large static rectangle. Logo detection can reduce the brightness of a persistent graphic. A screensaver or automatic display off timer stops adding exposure when nothing useful is happening. Brightness management reduces the electrical and thermal stress in the first place. Then there are compensation cycles, sold under names such as pixel cleaning or panel refresh. The display can estimate or measure how its pixels have changed and adjust their drive so the screen looks more uniform. Research systems model aging from operating history, current response, temperature, and predicted efficiency loss. In a curious piece of recursion, the screen may keep a numerical memory of pixel use to hide the physical memory left by the picture. Compensation is not molecular resurrection. It can correct differences while the panel still has enough adjustment range, but it cannot make degraded organic material new again. This is why normal maintenance matters. LG and Sony both document automatic protection features, including panel refresh, pixel shift, screensavers, and brightness controls. On supported LG televisions, the automatic cleaning process runs after the television is switched off and requires the set to remain connected to power, so turning an OLED off with the remote is useful. Cutting power at the wall every night may prevent the maintenance you were trying to protect the screen with. Manual refresh is a troubleshooting tool, not a ceremonial button to press after every film. Follow the instructions for the exact model. The names, schedules, and behavior vary. No protection feature cancels unlimited static exposure. It changes the rate, spreads the wear, or conceals part of the difference. The chemistry still keeps the final account. If your television spends its life moving among films, series, different games, sport, and occasional news, burn-in is unlikely to trouble most viewers. That is also the conclusion RTINGS draws from its mixed content evidence. The risk is not zero, it is distributed. If the display is an all-day work monitor with a fixed taskbar, the same window layout, bright editing controls, or dashboards parked in place, the risk is materially higher. The same is true for one news channel or one game with a bright, unchanging interface repeated for thousands of hours. For that workload, an LCD may be the calmer tool. It has its own aging and failure modes, but its pixels do not age through self-emission in the same spatial pattern. Choosing it is not an admission that you fear beautiful black levels. It is matching a display to a job. If you choose OLED, the useful precautions are pleasantly boring. Keep the built-in panel protection enabled. Let the screen turn off when idle. Hide or vary static interface elements when practical. Do not run ordinary SDR content at maximum brightness merely because the slider goes there. Allow the set to complete its automatic maintenance. Check whether the warranty for the exact model covers burn-in, because warranty language varies. Most importantly, think in repeated dose, not isolated accidents. Pausing a game for lunch is not the same as displaying its HUD for several thousand bright hours. Watching a news report is not the same as using one news channel as wallpaper for years. And now, the ghost on our grey screen makes sense. The old taskbar is not still shining. The surrounding pixels have a different history, and the uniform test image exposes the mismatch. An OLED can improve in materials, efficiency, cooling, and software, while still remaining vulnerable to uneven use. It can be a spectacular display, and a poor choice for one relentlessly static job. Both sentences can be true, without a fight in the comments section. Which is inconvenient, because it depends on your usage pattern, fits very badly on a warning sticker. But it is the honest answer. Your screen does not remember what the image meant. It remembers where producing that image demanded light, current, and time. Burn-in is that unequal work made visible. Stay silly.